Hello, this is Mrs. Ward, and I'm going to go over section 1.5, infinite limits. So what we're going to do today is determine the infinite limits from the left and from the right, and find and sketch the vertical asymptotes of the graph based on those infinite limits. So the definition of an infinite limit is if you have as you're approaching a number, if you continue up without bound or down without bound, then you're approaching a vertical asymptote. So you know what the graph looks like. It's kind of like you have this wall and your graph is coming along and it like splashes against the wall, but it can't cross that wall. And so this would be a limit as I would approach this 2 from the right. I'm going to say that this limit is approaching positive infinity. As this limit approaches 2 from the left, it looks like it's going down without bounds. So we're going to say that it's negative infinity. Um, and that's going to be how I tell that I have a vertical asymptote. One thing I want you to understand, though, is it's kind of funky, I guess. If you see that you have a limit that's approaching infinity or negative infinity, it means that the limit does not exist. You are just denoting that it doesn't exist because you have this unbound behavior as x approaches your number. So even though you're writing the limit as x approaches 2 from the left and you're writing negative infinity, if I ask you what the limit is, technically the limit does not exist. I know it's backwards, but that's just the way it is. All right, so example 1 is you have you're given -1 over x minus 1. I have this, when I look at this, x minus 1, if that's equal to 0, that's what's going to cause a problem or discontinuity. So when x is equal to 1 is where I have this vertical asymptote. If I were to ask you to denote some things, it would say the limit of f of x as x approaches this 1 from the left. So as I'm approaching from the left, I'm starting at my negative numbers and going here. That's going to continue in the positive direction. So I'm going to say positive infinity. The limits of f of x as x approaches 1 from the right. Again, coming from the right, we're coming this way, and that looks like it's going to negative infinity. Since I have since I have infinity and negative infinity, or they could both be infinity, both negative infinity, since my limits as I'm approaching that number from the left and the right is infinity, negative infinity, then I'm going to say that I have a vertical asymptote at, and then you have to write an equation in line. Oh, that's a really bad at x is equal to positive 1, and that's the equation of my vertical asymptote. So let's do, so the definition of a vertical asymptote is if f of x approaches infinity or negative infinity as x approaches c from the left or the right, then the x is equal to c is a vertical asymptote. So you have to be approaching infinity. You can't just have a discontinuity. It has to be a place where when you approach that number, you're going either up continuously or down continuously. So then they have this other definition for vertical asymptotes that says let f and g be continuous on an open interval containing c. If f of c is not equal to 0 and g of c is equal to 0, so your denominator is equal to 0, there exists an open interval containing c such that when g of x is not equal to 0 for all numbers that x is not equal to c in the interval, then the graph of the function is given by, when you divide, it has a vertical asymptote at x is equal to c. That just sounds so confusing. But what it's saying is if I have, let's say f of x is equal to, we're going to factor it for you, x plus 1, x minus 3, and let's say g of x is equal to, we'll say x plus 1 and x plus 3. All right, we'll go with that. So what this is saying is that if I have f of x divided by g of x, and f of x is not equal to 0. So if I have, there's two places where my denominator is equal to 0. One is when x is equal to -1. One is when x is equal to -3. Those are the two places where this denominator is equal to 0. If I put -1 into f of x, that's going to give me a 0 in the numerator. So that's what they're saying is that your f of x, where is it? f of c, and in this case f of -1, cannot equal 0, because that means my 0 can be simplified. It can cancel out. It becomes that open circle. I don't see it on my graph. It's just in the table that I see undefined. So that's what they're saying. So I'm not going to have a vertical asymptote at -1 because that simplifies. I am going to have a vertical asymptote at -3 because that one does not simplify. And when I put -3 into the numerator, I'm going to have -6, not 0. So if you substitute in, you get 0 over 0. That means, we've said this since we started limits, that means you can simplify that discontinuity and it becomes a hole in the graph and not an asymptote. If you cannot simplify where your denominator is equal to 0, then that becomes a vertical asymptote. Okay, moving on. So find the vertical asymptotes if there are any. So when I look at this, when I look at my denominator, x plus 3 is equal to 0. That I'm going to find the zeros in my denominator. Remember, 2 can't be 0 because it's 2. So I'm going to say x is equal to -3. If I were to put -3 in here, -3 would, I would have 1 over 0. So this is not 0, which means that this is a vertical asymptote. So I'm going to have a vertical asymptote, VA for short, at, has to be an equation of a line, x is equal to -3. If I were to verify this, I would pick up my calculator and I would graph, and then I would say, I would find the limits. So to prove this, I'm going to find the limits. Now, I could find the limits and show that they're approaching infinity, negative infinity, or both. The second one, when I look this, I'm going to try to find the zeros here. So that factors as x plus 1, x minus 1. The numerator does not factor at all, so nothing simplifies. So I'm going to have x is equal to -1, x is equal to +1. Since these are non-removable, they're both non-removable. If they're non-removable, they become vertical asymptotes. So my vertical asymptotes are going to be x is equal to -1 and x is equal to +1. Remember, non-removable become vertical asymptotes. Example 3, a rational function with common factors. So here in the denominator, that's factored as x plus 4, so x is equal to -4. But if I put -4 in here, I'm going to have 16 plus 32 minus 48, and I'm going to get 0, and I'm going to end up with 0 over 0 if I substitute -4 in, which tells me that I can simplify. So we're backtracking, and we are going to factor the numerator, and the numerator factors as x minus 12, x plus 4, and I kind of had a hint that x plus 4 was going to be one of my factors, x plus 4. Now the x plus 4's can simplify, and I'm left with x minus 12. So remember, this graph of f of x and this graph of, we'll call this g of x, are the same, exactly the same. The only place that they differ is at x is equal to -4. That's the only place that they differ, and the only way I'm going to see that there's a problem on the graph is if I go to the table, and at -4 it'll tell me it's undefined. Since the only place that I had the discontinuity, so it was discontinuous at x is equal to -4, that was a removable discontinuity. And since it's removable, that means there are no vertical asymptotes. So no vertical asymptotes for that one. For the next one, I have 2x minus x minus 15, and here I'm looking for when x is equal to 3 because that will make my denominator equal to 0. If I put in 3 in the numerator, that's 9, that's 18 minus 3 minus 15, so I'd get that 0 over 0 if I did put 3 in. That tells me that this can factor. It's basically telling me one of the factors is x minus 3. The other factor is going to be 2x plus 5 over x minus 3. Here the x minus 3's will simplify I'm left with 2x plus 5, so I'll call this g of x. So remember, f of x and g of x are the exact same graphs. The only place they differ is when x is equal to 3. So this graph is discontinuous at x is equal to 3. It is a removable discontinuity. I can't spell today. And since the only place that was discontinuous is removable, there are no vertical asymptotes. Okay, number 4, determine the infinite limit. So when I'm trying to find the limit as x approaches 2 from the right, I have the x squared minus 3x. This numerator can factor as x times x minus 3. The denominator x minus 2. It's discontinuous at that 2. It's not removable, which tells me I have a vertical asymptote. So I am going to pick up my calculator and graph that. So you should be graphing with me. I'm going to graph the x squared. I'm going to leave it as x squared. I'm not going to use the factored form. X squared minus 3x. And then my denominator is going to be x minus 2. And when I graph it, this is what I have. Remember, I'm looking at x is equal to 2. So let's just grab this so I can write all over it. So I'm just looking at the graph when I do this. This is 2 right here. Use a different color. This is 2 right here. So I'm going to say the limits of f of x as x approaches 2 from the left, and only once from the left. I'm coming from the left, so left to right. It goes like, looks like it's going up without bonds, so I'm going to say that it's positive infinity. Okay, the next one. Remember, you're just looking at the graph. Don't make this harder than it has to be. The next one, I have the limit of tangent of x as x approaches pi over 2. So I graph that, but right now it's in a standard window and I might not realize where pi over 2 is. So to help myself, I am going to change my window setting and I'm going to go to the trig because that makes sense to me. And so, and I want positive pi over 2. This will not move. Okay, apparently it's not going to move for me. So I'm going to grab this. So if this is 2 pi, then halfway through this would be pi, and then this would be about pi over 2. I want to approach pi over 2 from the right. So I'm approaching this line from the right, so I'm coming this way. So that's going to be negative infinity. So use that trig window because I think that does help you a lot. All right, so the properties of infinite limits, this deals with when you have the one limit approaching infinity or negative infinity, and then one limit approaching L, which would be a constant. So if I'm taking, this one's saying I'm taking infinity plus a constant, that should be infinity. If it were negative infinity plus a constant, it would be negative infinity. If I'm multiplying infinity times a positive constant, that's going to be infinity. If I take infinity and I'm multiplying it by a constant that happens to be negative, that would approach negative infinity. And that's what these two are saying. If I take a constant and I divide infinity, so I'm taking a number and dividing it by a larger and larger and larger number, that's when it's going to equal 0. So some of these are in order to find the limit sort of algebraically. So if I'm looking at this, I had the limit as x approaches 0 from the left. I'm thinking of the limit as x approaches 0 left of 1 plus the limit as x approaches 0 from the left of 1 over x. This is just going to be 1. And then when I graph this, so here's a graph of 1 over x. I'm approaching 0 from the left, so coming this way from the left, approaching 0. That looks like it's going to be negative infinity. So I'm going to have 1 plus negative infinity, which is just going to be negative infinity. So the limit of the entire thing is going to be negative infinity. Okay, the next one is the limit of x squared plus 2 as x approaches 1 from the left. So if I were to start this, and I would put in 1, and I would end up with 1 squared plus 2, which would be 3. And I did the graph of cotangent pi x, and it's just cotangent pi x, and that's this graph here. If I'm taking the limit as x approaches 1 from the left, so I'm looking at 1 from the left, it looks like that's going to be negative infinity. So this is negative infinity. So I'm going to have 3 divided by negative infinity. So I'm going to have a constant divided by a smaller and smaller number that's going to really get larger and larger. And this is just going to be 0. To verify that this is going to be 0, if I were to graph this whole thing, so that's the next graph I'm going to show you is the whole thing. I forgot that I can't do it that way. That's the whole thing. So if I'm looking at 1 and I'm looking at the place 1, this is the whole graph put together. I can see that at 1 it looks like it's going to approach 0, which is what I got here using the properties. So if it asks you to use the properties, then I kind of want to see the 3 over negative infinity. And so that's it. Here's your classwork or homework that you are going to do, and I will see this next time. If you have any questions, let me know. Know that there is a video already on Blackboard that goes over this homework, so if you have any questions or you get stuck, you can go and look at that. Okay, I hope this helps, and I will see you soon.